Where we left off in the last video, we were looking at the sources of marine sediment. Source number one is terrigenous, which comes from land. Source number two is biogenous, which comes from life. And those two are really the two biggest sources of sediment in the ocean by far. And we'll see that on a table in a few minutes. Our other sources of sediment, we have two more. The next one is what we call hydrogenous sediment. Hydro meaning water, so this is sediment that comes directly from the water and it precipitates out. And this happens typically when water evaporates, but it can also happen as a chemical reaction between different materials that are dissolved in the ocean. So let's take a look at the first of those categories, evaporates. When water evaporates, the material that's dissolved in it ends up in higher concentration. So the H2O goes into the atmosphere, which leaves behind the other things that are dissolved in the water. And that's going to be a topic of a future chapter, what is dissolved in the water, so seawater chemistry. But you probably know that sodium and chlorine are the number one and the number two dissolved solids in the ocean. Number three, it turns out, is sulfate, SO4. And calcium is another element that tends to be dissolved in a relatively high concentration in seawater. So when water evaporates, when seawater evaporates, very often we get a precipitate of sodium chloride. But we can also get precipitates of things like calcium sulfate, which you can see has a little water molecule attached to it, and that's the mineral that we call gypsum. And so this is an example of a place where a lake or a lagoon has evaporated and those salts are left behind. And sea salt is more than just sodium chloride and calcium sulfate. It usually has other other minerals in it as well. Now the other type of hydrogenous sediment is things that precipitate due to chemical reactions of dissolved materials. Now, technically that's what happens here when the water evaporates, but until the water evaporates, the sodium and the chlorine, the calcium and the sulfate are just going to stay dissolved in the water. Other elements, however, if they find a friend, you could think of it that way, if they find a friend, they can bond to that friend, and when they bond to that friend, they can form a solid precipitate and come out of solution or out of the water. One example of that happening are these manganese nodules. These are found on the bottom of the deep ocean. We don't know exactly what triggers their formation, but as you can see in this picture, there are some parts of the deep ocean floor that have large numbers of these manganese nodules. And they're called manganese nodules because they have a high concentration of manganese in them. But the other solids included in these nodules can include iron, copper, and a whole bunch of other elements. And you can see they seem to accumulate in layers. So they, as far as we can tell, they form very, very slowly over an extended period of time. In terms of scale, they can be around the size of a baseball. We have a couple of these at the college that you could look at, again, if we were face to face, but there are some nice pictures here in the book. The only thing they lack is a scale, but this is the size of something that you would probably be able to hold in the palm of your hand. So think of the size of a sort of a standard baseball. We have another similar kind of precipitate. This is calcite. Remember, we've already said that a lot of marine organisms use calcite in their shells, but calcite can also precipitate directly out of the water. And the conditions for doing this usually are similar to evaporate conditions, but it helps to have something that allows the calcite to be more concentrated in the water than it otherwise would be. As it precipitates out, you can actually get crystals of calcite, so you can get a sediment that's made of these pretty little crystals. But what's more common is it precipitates out as a really fine material that would appear to be mud. Under the right circumstances, and the right circumstances would mean that the water is shallow and there are some waves coming through. The waves can roll that mud into tiny little spheres that we call ooids, and you get what's called an oolitic sand. Now you'll notice that these are sand-sized grains, but they are a chemical precipitate of calcite. There are beaches in the Bahamas, for example, that are completely made of these little ooid or oolitic sand pellets. And we actually have a jar of these at the college. Again, unfortunately, you can't see them. These look a little rough on the outside. A lot of times the ooids are very smooth on the outside. The other interesting thing about the ooids is if you slice one open and look at it under a microscope or with a magnifying glass, you see layers just like you see on the manganese nodules. So again, these are another chemical precipitate that happens due to a chemical reaction in the water. So that's our third source, hydrogenous from the water. Our fourth and final source of sediment is going to be cosmogenous sediment, and the cosmos refers to space. So these are sediments that come from space. This is really the smallest quantity sediment in the ocean, or source of sediment in the ocean. But they're found all over the place. They are mostly microscopic. You can see these look like little glass beads because as they fell through the atmosphere, they got really hot and melted, and then they hit the water and they solidified almost instantly, and that's what turned them into little glass beads. And these are called tektites. But you can also think of meteorites and other objects from space would be included in the cosmogenous sediments. So what we want to look at next is just a little table, and this table is out of your book, and it shows you the percent of all ocean floor area covered by these different types of sediments. So the terrigenous sediments are number 2 in terms of percent of ocean floor covered. However, they are number 1 in terms of volume. So if we look at the total volume of sediment in the ocean, terrigenous would be number 1. Biogenous is number 1 in terms of area covered, but it is number 2 in terms of total volume. So they actually swap places when we consider volume instead of area. And we'll see that on a map in just a moment. The hydrogenous and cosmogenous sediments are in much smaller quantities. You can see 1% or probably less than 1%. And in most places, you won't find an area covered by cosmogenous sediments. That doesn't happen. They're in little amounts just everywhere. There are some places where you can find essentially the bottom of the ocean floor covered with hydrogenous sediments. You might remember that picture. Now, this is a combination because the manganese nodules, which are hydrogenous, are sitting on top of some kind of mud, which could be biogenous ooze, or it could be terrigenous mud. Could be either one of those on the bottom. But this is an example of a deposit of hydrogenous sediments. You can also see an area like a lagoon where the water is evaporating fairly rapidly, covered in a layer of hydrogenous sediments like this, like the salts. Or as I mentioned earlier, there are beaches in the Bahamas that are made completely of hydrogenous sediment as well. So there are some specific places you can go in the ocean and see deposits of hydrogenous sediment. There are not specific places in the ocean where you'd see a lot of cosmogenous sediment. This map shows us sediment thickness, and this is where we can explain a little bit about the terrigenous being larger or greater in volume. You'll notice there's some very thick sediment accumulation right in coastal areas, and especially where we have large rivers. For example, where the Mississippi empties into the Gulf of Mexico, you can see very thick sediment deposits there. And also from the rivers off the east coast of the United States, up here coming out of the St. Lawrence River. Over here, this would be coming off of some of the rivers that erode the Himalaya mountains, very big source of sediment. Right here, the Congo River, another big river dumping a lot of sediment in the ocean. This sediment off the west coast of northern Africa is primarily material that's been blown off the coast by the wind. And then over here, we can see some heavy sediment deposits associated with the Amazon River. So kind of depending on where you go, you can get a lot of terrigenous sediments delivered by rivers or the wind, and in some cases delivered by ice, so from glaciers pushing sediment. And you see that kind of sediment in some places around Antarctica, for example. The next category system that we'll use is the sediment location. And these categories are going to go a little faster, but sediment location, number one is neritic. And neritic, think of neritic is near the shore. So these are sediments that are found on the continental shelf. They tend to accumulate very rapidly, and most of them are terrigenous. They're brought there by wave action, glacial deposits, rivers dumping things in, and currents moving that sediment around. Most of the ocean, however, is deep water. It's far from the coast, and these are the pelagic sediments. And these are the sediments that we find on the deep ocean floor, most notably the abyssal plain. And this is a side view of the ocean. This is the continental slope and rise. And down here on the bottom, off the rise and onto the abyssal plain, you can see these very thick layers of sediment. This pelagic sediment, this deep water or deep ocean sediment, comes from primarily land and life. So those are the two biggest sources of sediment in the ocean. And where you find them more just depends on your location. And we actually have a map a little bit later on to go over that. The hydrogenous and cosmogenous sediments are visible in some places, especially the hydrogenous ones, because when you get onto the deep ocean floor, these pelagic sediments tend to accumulate very, very slowly. So how do they get to the deep ocean floor? Well, one way that they get to the deep ocean floor is through turbidity currents. And this is a way to move some larger material down to the ocean floor. If you remember back to that table in the previous video, the size of the sediment that can be moved depends on the velocity of the water. Well, it turns out that when you're on the continental slope and rise, because there's a bit of a gradient or a slope there, we can get some water moving so we can pick up the rate. And when it starts to move, it can pick up some sediment, and that muddy water becomes what we call a turbidity current. So the turbidity current is muddy water moving down the edge of the continental slope and onto the continental rise, and it then deposits the sediment on the deeper part or the pelagic part of the ocean floor. Some of these currents are constant, so they're constantly flowing off the shore, for example, off of a river. Some of them are generated by landslide events. If it's an event-generated turbidity current, it can produce what we call a graded bed, which they show down here in the bottom right-hand corner. And a graded bed simply means we have a layer that goes from coarse to fine material. And what's happening is during one of these landslide events, you can see in the upper left-hand corner here, as this moves out into deeper water and where it gets flatter, the water slows down. It drops the big stuff first because the water's slowing down, and then the finer materials get dropped off on top of that. So this is one bundle, this coarse to fine is one event, and it just shows us kind of what was happening to the velocity of the water. So we'll talk about some more pelagic sediments on the third part of this video set.